Hello, everyone. This is the Up and Running with Webassembly demonstration in our front-end weekly meetings. Today, I want to show you guys how you can implement WebAssembly in your web applications and use it as a performance boost. So let's go back in time. Actually, the birth of the JavaScript language time. So the JavaScript was created in 1995. And it wasn't designed to be fast. It wasn't supposed to be fast at that time, right? And the first decade, it was slow. So the language was created by Brendan Eich. He was an engineer in Sun Microsystems, and he was trying to make a scripting language for Netscape Navigator browser. And he wrote JavaScript in just 10 days. So he didn't think about optimizations. He didn't think about anything. He just wanted a language that resembles Java, hence the name JavaScript. And it was dynamic, it was easy to use, and it could be easily added to Netscape Navigator too. So after a while, where developers were using JavaScript and people were using JavaScript in their browsers, the JIT war begins. So the JIT stands for just-in-time compilers. And multiple browsers added just-in-time compilers, and JIT could see patterns in the code people wrote. And based on those patterns, it could make some assumptions and run the code faster. As a result, the execution of JavaScript was 10 times faster after the introduction of JITs into the ecosystem. And it made it possible for JavaScript not only run in browsers, but you can also, for example, get the V8 engine and put it on a server and you can JavaScript there. So that's how Node.js that's how Node.js was feasible to be built at the time. So let's talk a little more about the compilers and interpreters and what the differences are. Humans and machines don't talk the same language. So these arts are based on the Arrival movie. So on the right-hand side, we have an alien that talks in ones and zeros. He talks in the binary language, and the person in the right, she's using a high-level language containing high-level tokens like x equals a plus b, right? So if these two are going to talk to each other, they're not going to understand each other. So this is how interpreters can translate high-level languages, and also compilers also can do it. But the differences are with an interpreter, the translation happens line by line. So you don't read the whole thing. Line by line, you try to translate it and spit it out. And interpreters are quick to get up and running, so you don't have to go through the whole compilation, as I said, before you start running your code. And it made sense for the context of Netscape, and it made sense for the browsers to use interpreted languages such as JavaScript. But the catch here is when you're running the same code more than once, for example, if you're in a loop, then you have to do the same translation over and over and over again. Because you don't know what the whole thing is, you can't make adjustments and optimizations ahead of time. So the interpreter is doing its work during the runtime, and it cannot optimize the code and optimize its results. On the other hand, compilers read the whole thing based on some assumptions and based on some optimizations. It can generate a very well-defined binary that then we can use it, and it will be more precise and it will be more optimized than the binary interpreter spit out. So just-in-time compilers is the best of both worlds. So as a way of getting rid of the interpreter's inefficiencies in the browsers at a time, where interpreter has to keep retranslating the code every time they go through a loop or something like that, the browsers started mixing compilers in. So they introduced some kind of compilers that we will get into in the next slides. So they added a new part to the JavaScript engine called the monitor, also known as a profiler. And the monitor watches the code as it runs, makes a few notes of how many times it is run and what types are used. And if the same lines of code are repetitive or are being run over and over again, the segment code is called warm, and if it's run a lot, it is called hot. So based on those warm and hot places of our JavaScript code base, we can use two compilers, baseline compiler and optimizing compiler. So the first one being baseline compiler, when a function starts getting warm, the JIT will send it off to be compiled. So it is imprinted until we hit the warm section. And if you're hitting the warm section, we send that chunk of code to the baseline compiler. So it will read the code. It will make some assumptions based on that code that we just gave it, and the baseline compiler will make some of these optimizations. And however, if the code is really hot, as I said, it's going to be sent out to the optimizing compiler. So when a part of code is very hot, for example, you have a for loop that runs over and over again, it is being sent to this compiler. Let me give you an example. If we can assume all objects are created by a particular constructor. For example, we have an array of many objects, and they are all the same. So we don't interpret. If you want to map over it, for example, and change it to something else, we don't interpret it. We give it to the optimizing compiler and let it make some assumptions and make some optimizations for us. So the code is going to run faster than it would be if we give it to the interpreter. But as you know, JavaScript is dynamic, and there aren't any guarantees about the types, no pun intended. But the thing is, if the optimizing compiler or the baseline compiler is wrong about those assumptions they have and those optimizations they have, we can always trash their results and go back to the interpreter. So that's that. So here's where WebAssembly actually comes into play. WebAssembly is not going to replace JavaScript. It is the whole purpose of WebAssembly is that they coexist. Okay, so we load WebAssembly modules and we run it using a JavaScript API, and we offload some of the heavy work that we are doing to the WebAssembly. So is a way to run programming languages other than JavaScript on web pages, such as C, C++, Rust, and Golang. In the past, when you wanted to run code in a browser to interact with, all you have is the JavaScript, right? But using WebAssembly, we can introduce other kind of code bases into our web applications. We expect that developers are going to use both WebAssembly and JavaScript in the same application. WebAssembly modules define functions that can be used from JavaScript. So just like you download a module like Lodash from NPM today and call functions that are part of its API, you'll be able to download WebAssembly modules as well. I'll show you in a minute how it's actually done. So let's talk about why WebAssembly is fast. So this is how JavaScript execution timeline looked like back in the day. So first you have to parse it, then you have to execute it, and then after a long execution cycle, you're gonna hit the garbage collection to get rid of the unused objects. This is kind of how JavaScript works today. So there are a couple of different segments to this timeline. So we have parsing, we have optimizing and compiling, we have re-optimizing, we have execution, and we have garbage collection. Note this fact that these steps are not running one after the other. We may be parsing some of our JavaScript code, and at the same time, we may be garbage collecting or executing some other part of our codes. Okay, so this is just a very basic representation as if it happened in a timeline. So the parsing part, it takes a process of, we fetch the source code from the server in our client, in our browser, and we start to interpret it. And after compiling and optimizing, which includes the time that is spent on the baseline compiler and optimized compiler, as we discussed. So we need to re-optimize what those compilers give us. JIT spends time readjusting when assumptions have failed, as we discussed. And then the real execution begins and garbage collection at the end, just like the previous slide. We get rid of the objects we don't need. So this is different from WebAssembly, right? So the one in the bottom, the graph on the bottom, is the WebAssembly. So we just have to decode it, and we have to compile and optimize it, and just we need to execute it. So it doesn't, if you see it carefully, it doesn't include the re-optimized part. WebAssembly, because in WebAssembly things like types are explicit, the JIT doesn't need to make assumptions about the types based on the data it gathers during runtime. Because we are coding in C, C++, Rust, Zig, other strictly typed languages, and we are actually generating wasm files from those languages, we don't need to spend time on the re-optimizing part as we are doing in the JS world, because everything is any and everything is not guaranteed. And the other part is garbage collection. Because in those languages I just mentioned, we manually manage memory in those languages, right? So we don't need garbage collection for that. This is harder for the developer, but if you're going to make something like Figma, or if you're going to make something like AutoCAD run in the web, and if you're going to make a game for the web, you're already in a position where everything is hard and you have to manage everything on your own. So you're not going to need garbage collection. So that's that. So how is compiling to wasm works? So consider you have a file like written in C. I will show you in a minute. You have a file. You run this file through a compiler, which I'm going to use emscripten. The compiler takes in the code we just wrote in C and make it in an intermediate representation. Yeah. This IR means intermediate representation. And that intermediate representation is then converted into a wasm file. And that wasm file, we can download it and we can put it in the user's browsers. Why? Why is this wasm file a wasm module here? Because we're not sure what our users are going to use. What is the architecture of their machines? Is it x86? Is it AMD64? Is it ARM? What is it? We don't know it. That's why wasm is a kind of abstraction for a conceptual virtual machine that we can use. And it actually says what is actually possible in the x86 or ARM architectures. And it doesn't explicitly, it's not a target, it is not a target for our compilers. It is a abstract target for other architectures. So now let's get into the code, and I will show you in a minute how we can do it. So for example, we have a Fibonacci code base here. I just declared a function in C++. I called it fib. And what a function does, it spits out the nth number of the Fibonacci sequence. Okay, for example, it starts like 1, 1, 2, 2, 2 plus 1, 3, 3 plus 2, 5. So it's a standard Fibonacci sequence, and it spits out the nth Fibonacci number by using recursion. And I made sure I externalize this function so other modules can see it. And if you want to load this in a HTML, I have to first make a wasm module. Okay, so I'm using the EMCC, EM-Scripten compiler. I open up my shell, I write down this command, EMCC, we give it the file, and we wanted to make us the wasm module, then we can import that wasm module into our browsers and actually use it with a JS API. So I'm just going to run this. So it spits out some files. We are interested in the function.wasm file. Okay, I'm going to make a HTTP server running so I can load this index.html file. Okay, so this is an empty file, but we have the console, and I want to check if it downloaded the wasm file. So here in the HTML file, we're just using fetch normally here. So we are fetching the wasm file as an asset, then we are converting it to an array buffer, then we give that array buffer to the WebAssembly instantiate method that is available on modern browsers, and then we get the results. And after we get the results, we can use results, instance, exports, and we can use the method that we declared in the C++ file. Okay, so I'm just gonna check if it works. So it fetched the wasm module. So if I'm gonna show you guys, this is some instruction set. If you're familiar with assembly language, you're gonna notice some familiarity here. And so let's see if it altered. So I loaded the module, and this module includes two properties, instance and module, right? So in the instance module, we can see the exported functions from the C++. And as you can see here, we have fib, and we can call it. And we can call it with any number we want. I just wanted fourth number of the Fibonacci sequence, which is 1, 1, 2, 2 plus 1 is 3. So it spits out 3 here. So we can make this a little more beautiful, and we can say the 10th number of Fibo. And let's run it. So as you can see here, I think, oh, this is not the log. This is the log. Right. So 55. See how fast it executes? This is because it is compiled and it is run on my machine. It's not run in the browser. Of course, it is run in the browser, but it uses some optimizations and some APIs that are introduced with the WebAssembly API in the JavaScript world. So we can use it like this. Okay, so how is this interesting for us? For example, if you're a game developer, this is really interesting for us because you are already using very low-level languages such as C++, C, or other languages for that matter. So you can just compile your whole game in a wasm module and load it. And there are a lot of demos online. So they ported Doom, the game Doom, on the web, and it works very, very good. And but it is kind of heavyweight because the Doom I played on the web was 300 megabytes. So there are a little concerns about, for example, bandwidth and other things. But let me show you another thing. So here we have a this is so interesting. I found it on Hacker News. This is a blog, okay, for someone. It is a blog for someone. But if you, so there are a bunch of written content here, but if you want to see the search here, okay, so let's inspect the network. There's something interesting going on here. It fetches the SQLite3.wasm. So it uses SQLite on the client to fuzzy search through the contents of the web. So for example, I know this blog has something about Lisp. Okay, so I come here and I say Lisp. So let's monitor if it fetches anything from the web. Doesn't. And everything is blazingly fast on the client. So this is a very interesting use case of WebAssembly, and we can use popular modules that are run natively on our machines, and we can port it into the browser, and we can start using it there. So the other one is gaming, as I told you, and in real life, I believe Figma also uses WebAssembly to handle canvas rendering. And these are very great use cases of WebAssembly that I'm aware of. The WebAssembly is very well supported over the modern browsers, Safari, Chrome, Firefox, Edge, all of them support it, and it's very well supported. So to conclude this presentation, we talked about JavaScript history, we talked about compilers, we talked about WebAssembly and how we can use it to opt out of the JavaScript ecosystem for the compiling. And I showed you a very, very quick demo of how we can use WebAssembly and gave you some ideas about where it would be actually beneficial for us to use WebAssembly in our projects. Thank you very much for your attention.